As speech is one of the most remarkable human abilities, a complex dance of thoughts, breath, and muscle movements that we often take for granted. We open our mouths, and words simply flow, connecting us to the world and to each other. But for millions of people around the globe, this seemingly effortless act is a daily challenge. Stuttering, a condition that has puzzled scientists and society for centuries, interrupts this flow, creating moments of hesitation, repetition, and silence. For a long time, stuttering was misunderstood, often incorrectly blamed on anxiety, nervousness, or even a lack of intelligence. We now know that these ideas are fundamentally wrong and that the root of stuttering lies deep within the intricate wiring of the brain. In this exploration, we will journey into the fascinating world of neuroscience to uncover one of the most significant discoveries in understanding stuttering: its connection to a powerful brain chemical called dopamine. This tiny molecule, often famous for its role in pleasure and reward, plays a much broader and more critical part in how our brains function. It is a key messenger that helps regulate movement, motivation, and, as we are learning, the very mechanics of speech. By understanding the role of dopamine, we can begin to see stuttering not as a personal failing, but as a neurological condition with a biological basis, a perspective that transforms our approach to treatment, support, and compassion. Our goal is to demystify the science behind stuttering and dopamine, making it accessible to everyone. We will break down complex concepts into simple, understandable ideas, using analogies and real-life examples to illustrate the brain's inner workings. Imagine your brain as a highly sophisticated orchestra, with different sections responsible for various tasks. For speech to be smooth and fluent, every musician must play their part in perfect time. Dopamine acts as the conductor, ensuring the tempo is right and the transitions are seamless. When the conductor's signals are just a little off, the beautiful music of speech can be disrupted, leading to the blocks and repetitions characteristic of stuttering. This essay will guide you through the key structures of the brain involved in speech, particularly the basal ganglia, and explain how dopamine helps this system run smoothly. We will look at the compelling evidence from brain imaging studies and the effects of certain medications that support the link between dopamine and stuttering. By the end, you will have a clearer picture of why stuttering occurs, and more importantly, a deeper appreciation for the courage and resilience of those who live with it. This knowledge is not just for scientists. It is for parents, teachers, friends, and individuals who stutter, fostering a world of greater understanding and empathy. When we think of stuttering, we often picture someone repeating the first sound of a word, like please pass the salt. This is known as a repetition, and it is certainly one of the core behaviors of stuttering. However, the experience is much more complex and varied than this single example suggests. Stuttering, also called stammering, is a neurodevelopmental condition that disrupts the normal flow and timing of speech. It can also manifest as prolongations, where a sound is stretched out, such as "sometimes I feel stuck." Another common type is a block, where a person tries to speak but no sound comes out, creating a tense and silent pause before the word is released. These core behaviors are just the tip of the iceberg. Many people who stutter also develop what are known as secondary behaviors. These are actions they learn to use in an attempt to push through a moment of stuttering or to avoid it altogether. You might see someone blinking their eyes rapidly, tapping their foot, jerking their head, or clenching their fists. These actions are not part of the stuttering itself, but are coping mechanisms that can become ingrained habits over time. They are born out of the frustration and struggle of trying to get words out, a physical manifestation of the internal effort required to speak. Beyond the visible and audible aspects, stuttering has a profound internal and emotional dimension. Imagine knowing exactly what you want to say, but feeling physically unable to say it. This experience can lead to feelings of frustration, embarrassment, anxiety, and shame. A person who stutters might start to avoid certain words or situations they find difficult. They might choose a different, less precise word simply because it is easier to say. They might avoid speaking on the phone, ordering food at a restaurant, or participating in class discussions. This avoidance can limit social, academic, and professional opportunities, creating a significant impact on a person's quality of life. It is crucial to understand that stuttering is not a sign of low intelligence or a psychological problem. People who stutter know precisely what they want to communicate. The difficulty lies in the physical production of speech. The condition typically begins in early childhood, between the ages of 2 and 6, when language skills are rapidly developing. While many children naturally grow out of it, for about 1% of the population, it persists into adulthood. Recognizing stuttering as a complex communication disorder, with neurological roots and far-reaching emotional consequences, is the first step toward providing meaningful support and fostering a more inclusive environment for everyone. To understand the connection between stuttering and the brain, we first need to meet a very important chemical messenger, dopamine. You may have heard of dopamine in relation to feelings of pleasure and reward. It is the chemical that gives you a sense of satisfaction when you eat a delicious meal, achieve a goal, or receive a compliment. This is why it is often called the feel-good neurotransmitter. However, its role in the brain is far more extensive and fundamental than just creating pleasant sensations. Dopamine is one of the brain's primary neurotransmitters, which are chemical signals that allow nerve cells or neurons to communicate with each other. Think of the brain as a massive, intricate communication network with billions of neurons constantly sending messages. For these messages to get from one neuron to the next, they need a carrier. Neurotransmitters like dopamine are those carriers. They travel across a tiny gap between neurons called a synapse and bind to receptors on the next cell, delivering a specific instruction. This process happens billions of times every second, controlling everything we think, feel, and do. Dopamine, in particular, is a key player in a wide range of functions, including motivation, focus, memory, mood, and critically for our topic, the control of voluntary movement. The brain systems that rely on dopamine are essential for initiating and controlling our physical actions. When you decide to pick up a pen, it is the dopamine system that helps translate that intention into a smooth, coordinated movement. It ensures that your muscles contract and relax with the right timing and force. Without the proper amount of dopamine, movements can become slow, stiff, and jerky, as seen in conditions like Parkinson's disease, which is caused by a loss of dopamine-producing cells. Conversely, having too much dopamine activity can lead to uncontrolled, excessive movements, such as the tics seen in Tourette syndrome. This delicate balance of dopamine is what allows our bodies to move with grace and precision. The same principle applies to the incredibly complex movements required for speech. Producing speech involves the precise coordination of over 100 muscles in the lungs, larynx, also known as the voice box, tongue, jaw, and lips. Dopamine acts like the master conductor of this muscular orchestra, ensuring every component works in perfect harmony to produce fluent, clear speech. If the conductor's signals are too weak, too strong, or timed incorrectly, the symphony of speech can fall into disarray, providing us with a crucial clue to the neurological underpinnings of stuttering. Now that we understand the role of dopamine as a key messenger, let's explore the part of the brain where it does some of its most important work related to speech, the basal ganglia. The basal ganglia are a group of structures located deep within the cerebral hemispheres of the brain. You can think of them as the brain's central command center or executive manager for movement. They don't initiate movement on their own. That command comes from the brain's cortex, the outer layer responsible for thinking and planning. Instead, the basal ganglia receive these plans and then refine, sequence, and smooth them out, ensuring our actions are fluid and precise. Imagine you decide to say the word hello. Your brain's cortex formulates the idea and sends a rough draft of the motor plan to the basal ganglia. The basal ganglia then act like a quality control manager, checking the plan and coordinating all the necessary steps. It helps select the correct sequence of muscle movements for your breath, vocal cords, tongue, and lips, and inhibits any unnecessary or competing movements. It ensures that each sound is produced in the right order and with the right timing. Once the plan is perfected, the basal ganglia send it back to the motor cortex, which then executes the command, and you fluently say hello. This entire process happens in a fraction of a second, and dopamine is the fuel that makes the basal ganglia's machinery run effectively. The neurons within the basal ganglia are rich with dopamine receptors, meaning they are highly sensitive to its presence. A steady, balanced supply of dopamine allows the basal ganglia to perform its role as a gatekeeper of movement, selecting appropriate actions and suppressing unwanted ones. It helps regulate the go and stop signals for motor sequences, which is absolutely essential for the rapid alternating movements required in speech. Without the right dopamine levels, this gatekeeping function can become unreliable. When this system works well, speech is fluent and effortless. However, if there is a problem within the basal ganglia or with its dopamine supply, the timing and sequencing of speech movements can be disrupted. The go signal might be delayed, leading to a block. The stop signal might not function correctly, causing a sound to be repeated. This is precisely where the connection to stuttering becomes clear. The difficulties in starting words, the repetitions of sounds, and the involuntary interruptions in speech flow all point to a potential breakdown in the precise motor control managed by the basal ganglia, a breakdown that appears to be closely linked to how the brain uses dopamine. Given the crucial role of dopamine and the basal ganglia in controlling movement, scientists have proposed a really compelling theory to explain stuttering. It's called the excess dopamine hypothesis. Now, this theory doesn't necessarily mean that people who stutter have more dopamine in their brains overall. Instead, it suggests that their brains may just have an overactive dopamine system. This could mean that their dopamine-producing cells release too much of the chemical, that there are too many dopamine receptors on the receiving neurons, or that, well, the system for clearing away used dopamine just isn't working efficiently. The end result is the same: an excessive or dysregulated dopamine signal in the brain's speech-motor pathways. But how could too much of this important chemical actually disrupt speech? Let's return to our analogy of the basal ganglia as a kind of gatekeeper for movement. Dopamine helps regulate the go and stop signals. A well-balanced system allows for a smooth transition between these signals, letting planned movements proceed while inhibiting unwanted ones. If there's too much dopamine activity, though, it's kind of like the go signal is stuck on or is just firing erratically. This could disrupt the precise timing needed for speech, causing the brain to send conflicting or poorly timed instructions to the speech muscles. The result is a system that's hyper-excitable and, prone to errors. This overactivity can actually lead to the core behaviors of stuttering. A block, for instance, might happen when the system gets stuck, unable to smoothly transition from one sound to the next because of those conflicting motor signals. A repetition could be the result of the system getting caught in a motor loop, repeatedly sending the go signal for the same sound or syllable. It's a bit like a car's accelerator getting stuck, causing the engine to rev uncontrollably instead of smoothly moving forward. This model helps explain why stuttering feels so involuntary. The person isn't choosing to repeat sounds, but is experiencing a momentary breakdown in the brain's automatic motor control system. It's really important to clarify that this is a hypothesis, a well-supported scientific theory that continues to be researched and refined. It does not suggest that dopamine is the single cause of stuttering, since the condition is far too complex for such a simple explanation. Genetics, brain structure and function, and environmental factors all play a role. However, the dopamine hypothesis provides a powerful framework for understanding the neurological basis of the disorder. It shifts the focus from anxiety and psychology to neurobiology, opening the door to new research avenues and, most importantly, to potential treatments that target this underlying brain chemistry. For many years, the dopamine hypothesis was, just a theory based on observation and indirect evidence. However, with the advent of advanced brain imaging technologies, scientists have actually been able to look inside the brains of people who stutter and see this theory in action. One of the most powerful tools for this research is called positron emission tomography, or PET scans. These scans allow researchers to measure chemical activity in the living brain, including the activity of neurotransmitters like dopamine. The evidence from these studies has provided some of the strongest support for the dopamine stuttering link. In several groundbreaking studies, researchers used PET scans to compare the brains of adults who stutter with those of fluent speakers. They found that, on average, the group of individuals who stuttered showed signs of increased dopamine activity. Specifically, the scans revealed higher levels of dopamine production and availability within the regions of the brain associated with speech and motor control, including the basal ganglia. This was a landmark discovery, providing direct, visible evidence that the dopamine systems in the brains of people who stutter may indeed be functioning differently from those of people who do not stutter. Another type of brain imaging, called functional magnetic resonance imaging, fMRI, has also provided valuable insights. While fMRI doesn't measure dopamine directly, it measures blood flow in the brain, which is an indicator of neural activity. Studies using fMRI have shown that when people who stutter speak, there is often overactivation in certain motor areas of the brain, particularly in the right hemisphere. This suggests that their brains might be working harder or, less efficiently to produce speech. This overactivation is consistent with the idea of a hyperexcitable motor system, which could be driven by the dysregulated dopamine signals observed in PET scans. These imaging studies are incredibly important because they help move our understanding of stuttering from the realm of theory to the realm of biological fact. They show that the differences in the brains of people who stutter are real and measurable. This evidence is a powerful tool against the old, harmful myths that stuttering is caused by nervousness or psychological issues. Instead, it grounds the condition firmly in neurobiology, highlighting it as a difference in brain wiring and chemistry. This scientific validation is not only crucial for developing better treatments, but also for empowering individuals who stutter with the knowledge that their struggles are not their fault. Beyond brain scans, some of the most compelling evidence for the dopamine stuttering connection comes from a seemingly unlikely source, the pharmacy. The effects of certain medications on speech fluency provide powerful, real-world clues about the role of dopamine. For decades, clinicians and researchers have observed that drugs designed to alter dopamine levels in the brain can have a significant impact, either positive or negative, on a person's stuttering. This has allowed us to test the dopamine hypothesis in a very direct way, observing what happens to speech when we intentionally turn the dopamine dial up or down. The most supportive evidence comes from medications that block dopamine receptors, known as dopamine antagonists. These drugs are typically used to treat conditions associated with excessive dopamine activity, such as schizophrenia or Tourette syndrome. Researchers hypothesized that if stuttering is indeed linked to an overactive dopamine system, then these medications should help reduce stuttering behaviors. Numerous clinical trials have tested this idea, and the results have been consistently positive. Many individuals who stutter experience a significant improvement in their fluency when taking these types of medications. Their speech becomes smoother, with fewer repetitions and blocks. These medications are not a cure for stuttering, and they do not work for everyone. They can also have significant side effects, which means they must be prescribed and monitored carefully by a physician. However, their effectiveness provides strong validation for the dopamine hypothesis. The fact that a drug designed to reduce dopamine activity can also reduce stuttering is a powerful piece of the puzzle. It directly links the chemical action of the medication to the observable change in speech fluency, creating a clear cause and effect relationship that points squarely at dopamine's involvement in the disorder. This evidence has been instrumental in shifting the perception of stuttering. For a long time, treatment was limited to speech therapy, which is incredibly valuable for managing the condition, but does not address the underlying neurobiology. The success of dopamine-targeting medications has opened up a new frontier of treatment options, offering hope to many who have not found sufficient relief from traditional therapies alone. It reinforces the understanding of stuttering as a medical, neurological condition that can, in some cases, be managed with pharmacological intervention, just like many other brain-based disorders. This has been a game-changer for the field and for many individuals' lives. Just as medications that reduce dopamine can improve fluency, medications that increase dopamine can sometimes have the opposite effect. They can induce stuttering in people who were previously fluent. This phenomenon, known as drug-induced stuttering, provides another powerful line of evidence supporting the dopamine hypothesis. It shows us what can happen when the brain's delicate dopamine balance is disrupted, even in individuals who do not have a pre-existing predisposition for stuttering. It's a clear demonstration that altering this specific neurochemical pathway can directly impact the mechanisms of fluent speech production. One of the most common classes of drugs known to sometimes cause stuttering are stimulants used to treat attention deficit/hyperactivity disorder, or ADHD, such as methylphenidate, also known as Ritalin, and amphetamines, like Adderall. These medications work by increasing the levels of dopamine and another neurotransmitter, norepinephrine, in the brain to improve focus and attention. While they are highly effective for managing ADHD, a small percentage of individuals taking them report the new onset of stuttering-like behaviors. Their speech, which was once perfectly smooth, suddenly becomes marked by repetitions or blocks. This side effect often resolves when the medication is stopped or the dosage is lowered. Another example comes from medications used to treat Parkinson's disease. This condition is caused by a deficiency of dopamine, so treatments like levodopa or L-dopa are designed to boost dopamine levels in the brain. For many patients, This dramatically improves their motor control, reducing stiffness and tremors. However, in some cases, these dopamine-enhancing drugs can lead to dyskinesias, involuntary erratic movements, and can also trigger stuttering. This is a classic example of too much of a good thing. The medication overshoots its target, creating an excess of dopamine activity that disrupts the smooth sequencing of movements, including those required for speech. These cases of drug-induced stuttering are like a natural experiment that confirms the dopamine hypothesis from the opposite direction. If reducing excess dopamine helps stuttering and artificially increasing dopamine can cause stuttering, it strongly suggests that an optimal balanced level of dopamine is essential for fluent speech. This evidence is particularly compelling because it occurs in individuals without a personal or family history of stuttering, isolating the chemical change as the likely cause. It reinforces the idea that fluency is not just about anatomy or psychology, but about the precise moment-to-moment chemical environment within the brain's motor control centers. While the science of dopamine provides a crucial key to understanding stuttering, it is essential to remember that it is only one part of a much larger and more complex picture. Stuttering is not a one-size-fits-all condition. The experience varies tremendously from person to person and even from situation to situation for the same individual. One person might primarily repeat sounds, while another may experience long, silent blocks. This variability reminds us that while dopamine dysregulation may be a core neurological factor, it interacts with a host of other influences, including genetics, brain anatomy, and individual life experiences. One of the most well-known aspects of stuttering is its situational nature. A person might be perfectly fluent when speaking alone, singing, or talking to a pet, only to stutter significantly when speaking on the phone, giving a presentation, or talking to an authority figure. This does not mean that anxiety causes stuttering, a common misconception. Rather, the underlying neurological vulnerability is always present, but factors like stress, excitement, or pressure can exacerbate it. These emotional states can alter brain chemistry, including dopamine levels, potentially tipping an already sensitive system over the edge and making disfluencies more likely to occur. Furthermore, a person's thoughts and feelings about their stuttering can create a feedback loop that influences fluency. If someone anticipates stuttering in a certain situation, that anticipation can increase their anxiety. This anxiety can then make the stuttering more severe, which in turn reinforces the belief that the situation is difficult, creating a self-fulfilling prophecy. This is why comprehensive stuttering therapy often includes not only techniques for managing speech, but also cognitive approaches to address the fear and avoidance associated with speaking. It is about treating the whole person, not just the behavior. Ultimately, understanding stuttering requires us to embrace its complexity. The dopamine hypothesis is a powerful and enlightening model, but it doesn't tell the whole story. Each person who stutters has a unique neurological profile and a unique life story that shapes their experience of communication. Recognizing this complexity is vital for clinicians, researchers, and the public. It steers us away from seeking a single magic bullet cure and toward a more holistic and personalized approach to support, one that honors the individual's journey and empowers them with a range of tools to communicate confidently and effectively. Our journey through the brain has revealed the profound and intricate connection between the chemical messenger dopamine and the act of speaking. We have seen how stuttering, once shrouded in mystery and myth, is now understood as a neurobiological condition rooted in the brain's complex motor control systems. The excess dopamine hypothesis, supported by evidence from brain scans and the effects of medication, has fundamentally changed our perspective. It has shifted the conversation away from blame and shame and toward a scientific understanding that fosters compassion, validation, and hope for millions of people worldwide. This knowledge carries with it a powerful responsibility for all of us. For too long, individuals who stutter have endured misunderstanding, impatience, and prejudice. They have been told to slow down, take a deep breath, or just relax. Advice that, while well-intentioned, fails to recognize the involuntary, neurological nature of the condition. By understanding that stuttering is related to brain chemistry, not a lack of effort or courage, we can begin to dismantle these harmful stereotypes. We can learn to be more patient listeners, giving people the time they need to express themselves without interruption or judgment. For parents, teachers, and employers, this understanding is transformative. A parent can see their child's struggle not as a behavioral issue, but as a neurological difference that requires support and acceptance. A teacher can create a classroom environment where a student who stutters feels safe to participate without fear of ridicule. An employer can recognize that a person's fluency has no bearing on their intelligence, skills, or potential contributions to the workplace. This shift in perspective is the foundation for building a more inclusive and equitable world for people who communicate differently. Ultimately, the science of dopamine and stuttering is more than just a fascinating academic subject. It is a call to action for greater empathy. It reminds us that behind every moment of disfluency is a person with thoughts, ideas, and feelings to share. Our role as a society is to listen, not just with our ears, but with our hearts and minds. By embracing the science, we can replace outdated myths with facts, fear with understanding, and stigma with support. In doing so, we not only help those who stutter find their voice, but also enrich our collective human conversation.